Hi, my name is Todd Gayley. I work in kernel development at Wolfram Research. The title of my talk is Introducing the Wolfram Client Library for Java. This is a new Java library designed to make it very easy to call the Wolfram engine, whether the engine is running locally, in the cloud, and particularly with cloud-deployed APIs. Hello, everyone. My name is Todd Gayley. I'll be talking to you today about a new project I'm working on called the Wolfram Client Library for Java. So what is this library and why do we need it? Well, in the old days, there was Mathematica, and it was good. Being a user of Wolfram technology meant sitting in front of the Mathematica notebook front end and typing into it. Nowadays, though, we have Wolfram engine deployed in all sorts of different ways and all sorts of different places. In addition to desktop products like Mathematica and Wolfram Desktop, we have the Wolfram Cloud, we have Wolfram Enterprise private clouds. In particular, we have these cloud-deployed APIs. We've got Web Mathematica. We've got kernels running in mobile devices. We've got even more exotic things like kernels running behind a link server. And we've got other things coming down the pike. So what we really need, what users really need, is a simple and unified way to access this Wolfram language technology, no matter where it's deployed. Hence the Wolfram Client Library for Java. In particular, having Wolfram language technology available in the Wolfram Cloud means that you can write programs for yourself and for your colleagues, for your customers, that use Wolfram language functionality without requiring them to have Mathematica or any other Wolfram engine product installed locally. So we have all this great technology in the Wolfram language. We've got all these easy ways to deploy it and expose it to users. What we really need is libraries for a bunch of different programming languages that let developers call this from their favorite development environment. All right, so here's a curveball. You probably weren't expecting a slide about Wolfram Script in this talk. But I do want to take a little aside to talk about the relationship of this library to Wolfram Script. People maybe don't even know what Wolfram Script is. It's a command line tool. It's like a launcher for the Wolfram kernel. But Wolfram Script has some very interesting functionality that maybe people don't know about. These are just screenshots directly from the documentation on Wolfram Script. And you can see, if you say -code 2 + 2, then obviously it computes 2 + 2. This launches a local copy of the Wolfram kernel and executes the code there. But in the next line, this is where the magic happens. If you just say -cloud, that talks to a cloud kernel and executes that same code in the cloud. So here, with absolutely no effort and no change to anything other than putting -cloud in front of it, you're doing this magic thing of computing something in a cloud kernel. And you could also run cloud APIs. In this third example, very simply, you say -API, you give the URL, which has been shortened here, and then the arguments. And suddenly you've called the Wolfram Cloud API. Now, maybe people aren't all that interested in this. It's a command line tool. Maybe you don't care about command line tools. And obviously, it's limited in the sense that it's sort of textual input and output only. It's not really much for software development. But Wolfram Script is a unified interface to calling Wolfram technology in a very simple way. So Wolfram Client Library for Java and other client libraries, I mean, it's selling them short to say that they're just Wolfram Script for that other language. But in some sense, fundamentally, this is a little bit of the model for the Wolfram Client Library for Java. I want to be able to write a Java library. I want to give people a Java library that lets people call Wolfram language in different environments with essentially no modification of their code. All right. So this is a slide you might have expected to see in this talk. What's the relationship of this to Jlink? We have this Java library for many years called Jlink that is used to call Mathematica, call the Wolfram language. So the Wolfram client library is in no way a replacement for Jlink. Instead, it sits on top of Jlink. If you are using the Wolfram client library to talk to a local Wolfram kernel or any other kernel that you have attached to via a Jlink kernel link, that is MathLink or WSTP, then you're going to be using Jlink under the hood. It uses Jlink for all that functionality. it integrates fully with Jlink. That if, like I was saying, if you use Jlink, if you write some Jlink code that acquires a link to a kernel, which is what you do when you're writing Jlink programs in Java, then you can simply use that link as the target for your calls using the Wolfram client library for Java. You can go back and forth between writing sort of manual Jlink code to talk on the link or using the Wolfram client library API to communicate. Certainly, I think for users who don't need the slightly more advanced features of Jlink, the Wolfram client library for Java is going to be a little easier to use. But really, most important, it provides many features that are not in Jlink, like calling kernels in the cloud, either for APIs or direct computations for kernels. So really, it's the cloud stuff that is really the thing that Jlink doesn't have. OK, so in a slightly new direction for Wolfram, this is going to be an open source project. It will be made available on GitHub. It's not available on GitHub yet. If people maybe saw the Wolfram client library for Python talk earlier today, I guess they managed to get that on GitHub before the talk, so good for them. But good for them, I say. The Wolfram client library is not quite ready for its GitHub debut yet, but before long. And we certainly hope that others will contribute to the library. Is this large enough for people to read in the back? Because this is at 150%, and I don't want to have to zoom it. All right. So we plan to have client libraries for multiple languages. We're talking at this conference about the Java that I'm developing and the Python one that was talked about earlier. But we will write others in the future. We're certainly hoping that other developers will contribute libraries for other languages. Perhaps people will, writing in Java-like languages, will use the Java version as a bit of a model for theirs. Or if you're writing maybe in a more Python-like language, you might use our Python one as a model. All right, so here's some of the general design principles when I was writing this library. One is target independence. Now, target is the term I use in the library for the Wolfram engine that you're pointing at. So this is really the fundamental feature. I want to be able to write code that talks to a local Wolfram kernel, and you can change it to talk to a cloud kernel, change it to talk to a different target without changing essentially anything about your code. You just point it at a different place, and the code runs unmodified. In fact, my test file for this, hundreds of test cases, I just changed one line to point it at a different target, cloud local kernel, and it runs unmodified. You want to make it easy to send and receive native Java types. I don't want you to have to stringify arguments or something yourself or compose specialized things like JSON objects or something, unless that's what you've got. You want to be able to send and receive integer arrays, just native Java things, Java images, things like that. We will see this in the code later, but I encapsulate the result, any errors, and metadata in a result object. It's very convenient that way to have it all in a single object. And I don't throw, most of the methods don't throw checked exceptions. And this goes along with the previous thing. Instead of throwing an exception and having you deal with the exception, I return an object from every call. If there was an error, then the object is marked as not success, and you can interrogate the exception that was thrown by looking at the object. It also supports trivial change between asynchronous and synchronous evaluation. So if you want to start a call and have it return immediately and then later on interrogate whether the thing was finished, you can do that very simply. You don't have to worry about creating threads and managing that sort of thing yourself. And finally, I want a small and simple API. All right, so there's three main classes. One is Wolfram call, which is used to evaluate arbitrary code expressions. This is your evaluation function. There's Wolfram API call, which is used to evaluate APIs. It's a little different. You have named arguments and things like that in an API call. And the APIs of Wolfram call and Wolfram API call are almost identical. They're very, very similar. It's easy to go back and forth from one to the other if you know one. And finally, there's a class called Wolfram session, which represents a persistent kernel session. I don't think I'll talk about this in the talk because a lot of people will use this class, but it's just a way. Wolfram session is essentially a factory for creating these call objects. So you can read about it in the documentation. I won't really talk about it. All right, so here we go, some actual code. Can you see the colors? This is supposed to be sort of yellow, and this is yellow, this is green. I can see the blue, but I don't know if I see the, I worked so hard. It's all washed out. Oh, well. Yellow doesn't show up at all. All right, fine. Anyway, so here is a complete program. It's the only complete program I will show in this talk because no one cares about all this junk at the beginning and at the end. But this is an actual complete program that launches a local kernel and evaluates a trivial. Let's see if I can get this thing. Ooh, pointer. So I'm actually using colors to delineate 3 different sections. This is in this section where we sort of create the call and configure it. Here we perform it using the perform method. And then here in this final block, we sort of interrogate the thing and see what we got back. People might be confused about this notation here. It's really just one line. New Wolfram call dot set input 15 factorial. The methods in the Wolfram call class, they all return the Wolfram call object. So you can chain them together. You know, Wolfram call dot set this, dot set that, dot set this, dot perform. And I like that style of programming. It's very concise. But I often break a line like this, and you'll see that these lines will stack up in later sections where we're doing more things to the call. It's very convenient, and I think very readable notation. So we just create a new Wolfram call object. We set the input to be 15 factorial. It's supplied as a string in this case. Then perform is the method that does the work, and we ask whether it was successful. And if so, we get this Wolfram call result object is the thing that encapsulates the result and exceptions and metadata. And then we can interrogate it and get the result back. You notice it's a string in this case. The default result type is a string. And I respond otherwise. Now, I do want to point out that there's no Jlink here, right? There's no import Jlink classes or anything like that. We are using Jlink under the hood, but you're not dealing with that. You don't have to import any Jlink classes. Yes. Okay. Right. So the question is, what is the target of this Wolfram call? And the default target is a local kernel with the sort of guessed default path, which is, I'm cheating a little bit because I got the right path on my computer, but lots of people would have to use a path in the Wolfram call constructor to point to the correct kernel. All right. So there we have it. Very simple program, a complete program. All right. So that was the evaluate this thing in a local kernel. So what if I want to point at a cloud? I want to ask the cloud to evaluate this. I got all this pink that's supposed to delineate the changed bits. Can you see that? This chunk is a different color. Okay, good. It's probably too bright or something. Anyway. Oh well. All I have to do is I call set target and pointing at the cloud-based URL of the Wolfram cloud. Now there is a constant in the library that is this URL, but I put it in the code here just so you can see it more clearly. So I simply add set target cloud, and then everything else about the program runs exactly the same. So this is like the dash cloud in the Wolfram Script example, right? So that's simple. I just call set target, and I point at a different execution engine. So the possible targets for this, well, a path to a local kernel. One is a Jlink kernel link object. So if you use Jlink to, mathlink factory.create kernel link, all that. If you use Jlink to acquire a kernel link, then you can simply use that as the target for one of these Wolfram calls. Or as I just showed, the cloud-based URL to the Wolfram cloud, or your own private cloud. All right. So now I'm going to shift gears because there's lots of features of this library, but I'm going to show them really in the context of an API call. It's probably a little more interesting. So we're going to jump now to using Wolfram API call, which is the class. Yep. Oh, you're giving me that. Right, so calling cloud APIs, that's what Wolfram API calls about. So targets, there's a public cloud, that's the default target, but you can also point at a Wolfram Enterprise private cloud and other things that we have coming. All right, so here we go. So in these slides, usually at the top, there's a cloud deploy command, which deploys some simple API, and then I'll show a program that calls it from Java. So here's a trivial cloud deploy. It just takes one argument called X, it just squares it. And you notice I say permissions goes to public just because I don't want to have to deal with authentication and permissions in this code at the moment. So one way to specify the endpoint for this call is the set UUID function. See, lots of people, they don't realize that you can name your APIs, so they get these horrific UUIDs in the API name. But if you do that, then you can just say set UUID and put that ugly string in there. So we just create the call, we set the endpoint for the call, and then we add an argument called X with the value 42, perform, and it's exact same. The rest of the code is exactly just like a Wolfram call. So let's look at some argument type flexibility. So here, in this case, we have a cloud deploy. It just takes 4 arguments, W, X, Y, Z. They're all integers. It just multiplies them together. And here I give it a sensible name. So here's how I prepare the call. I call set endpoint. I give the endpoint minus the prefix, which I can leave out. So here you notice I can give an integer. I can give a string that will turn into an integer. I can give it a Java integer object, and I can give it an expr that represents integer. Expr is a Jlink class that represents arbitrary Wolfram language expressions in Java. So I have flexibility in how I specify it, and I slipped another feature in this thing, the set result type. In the past, we were always getting results back as strings. That's the default result type. But if I want an integer, if I expect this API call to return integer, I can say set result type.integer, and then you notice here when I get the result, I cast it to an integer. It will be an integer. And I know this cast will work because if this thing can't, if an integer couldn't have been created by this call, then an error would have been thrown, this not success. This success thing would not be true. So we have flexibility in how we supply the arguments. Now this is a simple example, but if you had an API that took arrays or something like that, you could pass the same sorts of arguments, exprs that represented arrays or native Java arrays. So this is just the enum class in the library that shows all the different result types you can specify. Expr, which is very convenient to represent anything. Expr class is very good if you get something and you want to send it back. You don't really care what it was, but you want to send it back as an argument to the next call. You just get something as an expr and pump it in as an argument to a future call. Then you can say string, binary, which is an array of bytes. An image, you can directly say image and get a Java image back, various things. So here's an example of using the result type image. So here in this API, you notice that it's a plot command. So you notice this third argument, JPEG. This is the export form argument for API function. So this API is written to return a picture. So when I'm calling an API like that, I just say set result type image. And then you notice in the get result thing will be a Java image object. And then I do whatever I want with this, display it or something like that. So it's trivially simple to get back an image. All right, so the slide has to be open because I have to give a little preamble to this. Those result type specifications, result type integer, they don't coerce the result into something of that type. They say, I'm expecting to get something like this back, and when I call get result, I want it to be cast to that type. That previous API that returned an image was written to return an image. But what if you have an API that is not written to return an image, but I've decided that instead I want it back as an image, right? There is a way in the cloud deploy API to specify, to allow users to specify alternate export forms for their things. And it's a little tricky. You have to know about this allowed cloud extra parameters. So you see this allowed cloud extra parameters goes to underscore export form. So you have to tell your API, I will allow people to specify alternate export forms. It's kind of obscure. In fact, I'm writing the specific one, but it's really easier just to say allowed cloud extra parameters goes to all. I mean, it's not the default because it might be considered a security risk. Let other people call your APIs, which are running on your dime, and export it to something else. Maybe you don't want people using up cloud credits to convert something to some other format. But if you specify this when you deploy it, you specifically allowing export form changes, then you put this in the thing. So anyway, here it's the same thing, but here I say set export form JPEG, and then in result type image, and I'm getting. The thing to note here is that the author of this API did not write it to return an image. Okay, I mean, yes, it's a plot command, but if you did this without setting the export form, you'd just get a graphics expression back, right? This could be 2 + 2, and if you did it, you'd get a picture of the number 4 instead of the number 4 back. So you have the ability to specify an alternate result form than the author of the API put in there originally, if they deploy it in such a way that gives you callers permission to do that. Okay, we can also do asynchronous execution. Here's some API that takes a long time. There's a limit on how long cloud APIs can run, but let's just say it's at least a few seconds. So the only thing I do differently is I call perform async. And instead of getting back a Wolfram call result, I get back a future of a Wolfram call result. Future is just a standard class in the Java language. It represents a future result. And the future interface has methods like isDone. So later on, I can interrogate whether it's done. It has a method called get, which returns the result. If I call get on a future, it will block until the thing returns. So I might, periodically interrogate whether it's done and call get if I don't want to wait, or I can just call get right away and wait for it to return. But the point here is that I don't have to mess with threads, right? Of course, a thread is spun off in the background to perform this call. I don't have to deal with any of that. I just say perform async. I get a future back, and I can interrogate this future, use it how I want in the rest of my code. Just some quick examples for authentication permissions. Here's an API that was there was no permissions goes to public here. So this is a private API. So one way, I want to call my own private APIs. One way to do it is I can call generate secure authentication key. And I get something back, a secure authentication key that has fields for key and secret. And so I would look at this object, and I would, I just do this once in Mathematica while logged in. I get a secure authentication key that represents me. And I take the strings from this key, and I can put them into my Java program and with the set auth credentials and call these private APIs. Another way to control who can call your APIs is to use this permissions. Permissions goes to permissions key, somekey goes to execute. So what I'm saying here is that anyone can call this API as long as they provide this permissions key known as somekey. And so if I have I can call set permissions key somekey, and then I'll be able to call that API from Java. You could also receive evaluation metadata. And that includes extra things like the timing information. You can get any print or messages that were generated during the API. This is extremely useful because lots of times something doesn't go right. You have no idea to figure out. You get something unexpected back. If there were any messages issued, you can determine what they are. Now, again, for this, you have to. This is also one of those allowed cloud extra parameters. The deployer of the API has to allow you to change the response form. So this doesn't work for any old API, but if I had said, if you just say all here, it's a little bit easier. But just say allowed cloud extra parameters goes to all when you deploy your APIs and save yourself a lot of hassle. So again, we just say set collect evaluation data true. And if we do that, then the Wolfram call result object that comes back has get metadata. It will have metadata in it. You can get the metadata out, and you can get, this is actually incorrect. String, it is an array of strings, and prints is an array of strings. So you can get any messages and any print output generated, and you can also get the timing of the thing. don't really have time for my demo, but maybe I'll run it anyways, because I don't have anything after this. So let's just trivial example of a interesting cloud API that maybe you want to expose to users. I've got, maybe you've seen that Wolfram language has this ability to take images and modify them in all sorts of interesting ways automatically. So I'm calling this Goghization, right? So this neural network can take a picture and kind of make it look like a Van Gogh painting. So all I have to do to expose this incredibly cool piece of Wolfram language functionality to the world is say cloud deploy, API function. I say that it takes one argument called im, which will be understood as an image expression or image data coming in, and that is the code for the API. I just called net model, applied it to the image, and I say I want to return a picture, and that's it. So if I've deployed this now, how do I call it from the Wolfram client library? Well, anyway, here's an example picture, lovely picture and here's what the code looks like in Java. So this is the only thing that you would need to write to call that API. And I also want to point out that all this code here at the bottom is just sort of boilerplate Java for displaying the image, right? And this is just boilerplate Java for reading it in off the disk. So this just reads this image file off my disk, set endpoint, add argument, set result type image, perform the call, get the result. It comes right back in as a native Java image, and then I just use some standard Java code to display it. I'm not going to run this as a Java program because I don't want to write Java programs. Instead, I'm going to write a Jlink program. I'm going to run this while I'm talking. It takes a few seconds here to launch and set up. But there we go. So that's what that thing looks like. So maybe, this is a pretty useful thing. You maybe want a little Android app that lets people take pictures and press a button and they get a little Van Goghization of the picture. It's that simple. It's just a handful of lines of Java code. This magic here, this is just, instead of writing a Java program and compiling it, I'm writing some code in the Wolfram language that uses Jlink to call my Java library, right? This is not the local mathematic evaluating this. I'm literally using the Wolfram client library for Java. I'm just calling it from mathematic using Jlink because I don't want to leave the mathematic environment from my demo. So anyway, it's literally just a handful of lines of code to produce this program. I guess. All right. Conclusion, look for it on GitHub before long. Thank you very much.